Hello, in the last videos we discussed some problems on Debian trees. Let's discuss the next one. Here is the question, read it and give it a try. You are part of Uber's infrastructure team optimizing a network of microservices modeled as a tree. Each pair of connected services, UI and VI, exchange the data with a load cost service V of I. To avoid overloading any service and to ensure smooth performance, no service can handle more than k direct connections. You are allowed to remove any number of edges to meet the constraint. The network may disconnect after pruning. So the question is saying that given a tree, we can remove any number of edges so that after removing any number of edges, the final tree can have any node with at most k connections. And finally, after removing any number of edges with making this constraint true, and then we have to return the maximum sum of weight of edges left in the tree. And constraints are the number of nodes is up to 1 if I, and the k where every edge should be at most connected to this number of other nodes is also up to 1 if I. So given a tree, we can remove any number of edges, and after making all the changes, any node should have at most k connections, and if that is the case, then it is a possible tree. And then if there are many possible trees, then we have to return the maximum sum of weight of trees edges that are left in the tree. So for example, this is a given tree and k is 2, so any node can be at most connected to other nodes. So if this is the given tree, one of the possible ways to remove the edges are this and this. So if these both are removed, then it is connected to this and this, and so this is connected to 2, this is connected to 1, this is also to 2, 1 1, this is 0, and this is 1, and this is 0. So in this way, we are sure that every node is connected to at most 2 nodes. It does not mean that a component size should be less than or equal to, it just means that it should be directly connected to at most 2, not in the indirect way or not in the component wise. A component can have any number of, this is also a possible tree finally, even if k is equal to 2, because every node is directly connected to at most 2. So if this is a small example, then if k is equal to 1, it means that any node can have only at most 1. So if we remove 3, then it can be both 5 plus 4, which is the maximum possible 9. So we have to return 9. So first thing is greedy. So let's try to think about the very trivial solution that we can think of. And if it does not work, then we'll try to think more. So what is the first thing? Then the first thing would be obviously removing the edges with least weight. So let's take this example, and now we are thinking that why it is wrong to select edges with least weight, because removing the edges with least weight will ensure that the final edges will be of more weight, and which is we exactly want. So if this is the tree and if k is equal to 1, so we should remove edges such that any node is connected to at most 1. So we can remove these both, we can remove edges weight 2 and 3, so that finally this is the final tree, maybe disconnected tree, and then each node is connected to at most 1. So if this is the final tree, then what is the answer? The answer is simply 4, because we removed 2 and 3, the edge left is 4, this is 4, so answer is 4. So this is the way that we think of originally, because we thought that we are removing the edges with least weight, so remove 2 and 3, so we thought that the answer will be highest. But what if we directly remove 4? So in this way, the final edges will be 2 and 3, and the sum is 5. So from this we can understand that greedy will not work, because even if we are trying to remove with the least one, if the case is like 3 4 5, the sum of two least is more than the highest one. So our choice will fail here. So we cannot think in terms of greed. So now let's think of other ideas. So for now, let's assume that the random node, the root of the given tree is some random node, because it is given that it is not rooted 0 or 1 or any other node. So for now, we just think that the tree is rooted 0, and we'll think of other later. If we can achieve the solution with this, then we can think of the other. Now, so assume that this is the given tree. This is connected to 1 to 3. These are connected to many other subtrees. And now if k is equal to 2. So if k is equal to 2, and we are thinking about 0 as node, 0 as root. So start from root every time. So we are at 0 and we are thinking that any node should be connected to at most 2. But adjacency of 0 returns 3 because it is the size of 3. It is the size of adjacency of 0 where it stores 1 to 3. So the size is 3 but k is equal to 2. So we have to remove some edges, right? Because each node can have only at most 2 connections. So our adjacency size is 3, so it means that 0 is connected to 3 nodes for now and k is equal to 2. So we have to remove 1 edge. So what are the possible cases? We can remove 0, 1, we can remove 0, 2, we can remove 0, 3. So for now let's assume that we are removing 0, 1. So if we are removing 0, 1, then what are the consequences of this? What should the rest of the tree be updated? So we remove 0, 1. So if we remove 0, 1, then one should be informed that the edge with parent 0 is removed, right? Because every node should have the constraint that it should be connected to at most k. But if we are thinking only with respect to 0, then how can one know that whether the parent edge is there or not? There are two cases. If we remove 0, 1, then one should be informed that there is no more parent edge, so that it will reduce the size of adjacency list by 1, which means that the edge is already disconnected. So it is connected to only adjacency size of adjacency list dot size minus 1 number of edges. And if the other case, if 0, 1 is not removed, if 0, 2 or 0, 3 is removed, then even then one should be informed that the parent edge is not removed. So indirectly it is like 1 is connected to 4 nodes. So then we can think what are the edges to be removed. So for every, so if we are thinking with respect to root node, then obviously when we are taking the choice as a root, then we have to inform the child that whether parent edge is removed or not, so that it can make the decisions based on this boolean. So now what is the function that we want? Because we assumed that we are starting from the root. So from root we will return some function of node comma that. So what is the function till now? The function is simply the node which we are and is the parent edge removed. So by this we can get the answer. For example, we have function of 3 comma 1. So what does function of 3 comma 1 implies? So this means that the answer for subtree rooted at 3 when the parent edge of 3 is removed and when the tree is rooted at 0, because we are thinking only with respect to the root as 0 for now. So what does function of 3 comma 1 means? This means that when the tree is rooted at 0, the answer for subtree rooted at node 3 and the parent edge is already removed. So this is the case for function of 3 and 1. And next thing is we already discussed. So how many edges can we remove from 3? Can we remove from a given node? So then we can, so it means that for example the adjacency list size is 5 and if the parent edge is removed, so if this is 5 and if the parent edge is removed, so then indirectly it is like what? It is simply like it is connected to 5, it is originally, so 4 children and 1 child, one root, one parent node. So now if the boolean is 1, it means that the parent edge is already removed, so it means that it is connected to only 4. So if it is connected to only 4, then what is the number of edges that need to be removed for this node? So only k can be the maximum one. So if k is equal to 2, then what are the number of connections we have to remove? It is k, it is the edges in the list minus 2. So in this way, based on whether the boolean is true or not, we can get the number of children that we need to be removed for a given root. So we discussed that if parent edge is removed, it means already the edge got removed. So indirectly we can save the edge. And similarly the other one. So for example, let's discuss again. For example, this is the given tree and we are at this node. So if we are at this node, what will be the adjacency of this dot size? It will be 4 because it is connected to 4. So this is 4. And for now, let's assume k is equal to 2. So we can remove 2 edges because we can have only 2. We have 4. So we are removing 4 minus 2, which is 2 number of edges. But if the parent edge removed boolean is true, so it means that it is indirectly removed. So the size is only 3. So then we can remove only 1. We can remove only 1 before we can remove 2. So the boolean helps in 2 ways. The first one is to inform whether the parent edge is already removed or not. The second one is indirectly both are same, but the second one is what are the number of edges that need to be removed for node given the information from the parent. So in this way the boolean will help. And now we got how many edges to be deleted for a given node. So based, for example, we have function of x comma boolean. So from this we got the number of edges that need to be removed from x to x of child given boolean. And now, but we got the number of edges to be deleted, but which edges? Because for example we have 10 children and we are going to remove 3. So which 3 we will select, which 3 we will not? So for now let's take again the simplest case ever possible. So let's assume we have to remove one edge. For example we are at 0. For example we are at 0 and we have 2 children, and for now let's assume that we are going to remove one child. So k is equal to 1, so we are removing anyone, whether it is 0 1 or 0 2. So check the first case. If we are removing 0 1, so if we are removing 0 1, what will be the final answer? So if we are removing 0 1, so what is the answer for subtree rooted at 1? It is simply function of 1 comma 1. So one is the subtree rooted at 1 and second one is a boolean that 0 1 edge is removed. So this is the answer that will be returned from subtree of 1. So this is one part of the answer. And now what is the rest part? So subtree of 2, this is also the other part. So for 2 we are keeping 0 2 in the final tree, we are not removing this. So it will be simply function of 2 comma 0 with respect to root 2. So these both are considered. And now coming to 0. So coming to 0, we are removing this. So finally 0 to edge will be there. Now let's assume that the weight of that is W02. So this is the final answer. Function of 1 comma 1 is because of subtree rooted 1. Function of 2 comma 0 is answer subtree rooted at 2. And W02, it means that the answer for the present root node. So in this way we can cover the whole answer. So this is the answer when we remove 0 1, and similarly exactly the opposite case when we remove 0 2. So function of 2 comma 1, because we are removing 0 2, so this is removed, so function of 2 comma 1, and then function of 1 comma 0 because it is not removed, and then W01 because we are removing 0 2, we are preserving 0 1 in the final tree. So these both are the values that are left when we remove two possible choices. So let's do some math behind this and observe which one to remove and which one is not removed. So compare both. So this is the first value when we are removing 0 1, and this is the second value when we are removing 0 2. So for now let's assume that 0 1 is greater than 0 2. So we'll assume that 0 1 is greater than 0 2, and then if we get some formula, then we can think that this is better for greater than case. So let's take an example and we can understand better. So this is greater than this, so assume that this is greater than this. When it will be greater, so make all the parameters with respect to node 1 aside and with respect to node 2 aside. So function of 1 comma 1, so this is related to subtree rotated 1, so bring this in the left side. And function of 1 comma 0, so this is also with respect to node 1, but the boolean value is different, but indirectly this is referring to the subtree of answer. This is referring to answer of subtree rooted to 1. So function of 0 comma 1, this is also related to node 1, and W01, so this is also related to node 1. So we brought all these in the left side, and similarly function of 20 W02 and function of 21 will be right side. So these all are related to 1 and these all are related to 2. So from this we are able to make two separate functions for each node, right? So for example we have x greater than y. So in this way x is one variable and y is other variable. So if we are able to make in this way, we can directly conclude. But for example we have x square plus 2xy square is some greater than y square plus x cube something. So if this is the way, then we cannot try to make some function of x and some inequality with function of y, because we have xy term and we cannot separate. So we have to do some graph for this. But now it is not the case. For now we got all the terms with respect to one node aside and with respect to other node aside, which is very useful, because if we have many other different nodes, then we can simply find the each unique value for every node, because it is dependent only on that node. For example, if we have node 1 and we have all the information with respect to 1, then we can directly find this, because these are not related to any other node. It is simply related only to node 1. So we can find answer for 1, and similarly we can find answer for 2 and so on. So this is very beneficial because we're able to make some hash functions for every node, so that it is not dependent on any other nodes. So it is better to remove 2 if some hash of 1 is greater than some hash of 2. Why is this? Because so this is the final answer, right? This means that this is greater than, so final answer when 01 is removed is greater than the final answer when 02 is removed. So which will remove then? Obviously we'll remove 02 because we are getting more profit when we are removing 01. So removing 2 is better if the hash function we found above for 1 is greater than the hash function for no for 2. So hope you got this, because we discussed already. If the value, the final answer for 01 is greater than 02, so what does it mean? It means that the answer is better if we are removing 02. So based on the values, then we can determine which one to remove or not. So now we got for 2 nodes. So for now, let's assume we have 3 nodes. So it means that we have 3 child nodes and we are deciding which nodes to remove, which edges to be removed. So for example, if hash of 2 is greater than hash of 3, is hash of 2 is less than hash of 3, and hash of 3 is less than hash of 1. So in this case, it is better to remove 2 first, and then if still, for example, if k is equal to 1, for example, if the number of edges deleted is 1, then we will simply remove the edge with child 2, and if it is 2, then we will remove this also, and if it is 3, we will remove this also. So in this way, if we have many different child, we can find the hash function of every other children, and then we can sort with respect to hash function of that node, and then we will get the final children based on the hash function, and then we can sort with respect to smallest to least, smallest to highest, and then based on the number of children need to be removed, we will come from the list and we'll remove how many required. So it is simply hash of node is function of node comma 1 minus function of node comma 0 minus weight from parent with respect to that node. For example, this is the 0 and this is 1. So what is the hash function of 1? It is simply function of 1 comma 1 minus function of 1 comma 0 minus weight of this edge. So from where we got? We got this from this one, from this inequality. So this is just nothing but the final way which we are removing the children. So let's say we store a hash of all nodes in the vector and sort it, but we have to add, and also let's say we have 3 children, right? So we have 3 children, and so one other thing is, for example, we are finding the answer for node. So how can we find the answer for this? How can we find hash value for this node? So it is dependent on its children nodes, right? So it is dependent on function of node comma 1 minus function of node comma 0. So these both are indirectly related to children. So from this we got that we are using DFS. So for this node to get answer, we will call this one first, and then we will call all the children. And then when we complete answer for all the nodes, then we will reach this. When we are reaching this, we already have the function of this node comma 0, function of this node comma 1, and this also, this also. So when we are reaching this, then we will have all the information required for all the nodes, and then we will find the hash of these all again, and then we will sort, and then we will make the discussion based on for the present node. So for the, when we are at root node, we want answer for children. So we will call the answer for children. We will complete the DFS for all the children, and then we will start thinking about this node. And now coming to next one. For example, this have 3 children, and function of this node comma 1 is 3. Function of the, this is function of node comma 1, and this is function of node comma 0. So let's assume that these are the values 3, 4, 6, 2, 7, 1. So if these 3 are the values, then we will find the hash function of all these, we will sort, and then we can get. But only hash value is required. For example, what is the hash value of this? And let's assume this also. So let's assume this is 3, this is 5, and this is 6. So we got hash values of these also. So if we blindly store only hash values in the vector and we sort it, we can get only hash. But finally we are not adding the hash values to answer. We are adding whether which one is better. For example, let's check this one, right? So let's assume these are the nodes based on hash value sorted. So we have to remove 3 edges. So we'll come from the list one. So we'll delete. So D2 is the answer when we are deleting the present edge, and now ND is the answer when we are not deleting. So these are the answers that we got when we done DFS for that. And now we are at the root node and we are thinking about which child element to remove. So we found the hash, we sorted in the ascending order, and then we got that we are removing 3. So we are coming from list. So we are coming from list, right? So coming to 2. So this is the first edge that we are deleting. So if we are deleting, what is the answer that we need to consider with respect to 2? Because this is 2 and this is subtree of 2. There can be many other big subtree also. This is 3 rooted at sub 3 and this is 4 and so on. So from 2 we can have two type of answer. One is function of 2 comma 0 and function 2 comma 1. So which one to consider an answer? We can either consider only one, right? If we are removing this edge, then we have to consider 2 1. If we are not removing, then we have to consider 2 0. So for now, which we have to consider, we can either select only one. So here we are deleting 2 because it's the least one, so we are deleting 2. So in these both we will consider D2 for this because we are deleting. So for 2 the final answer is D2. So D2 plus, and we are deleting this also because we have to delete 3. So we are deleting 3, so D3 for this also. So this is D3 and then D1 also because we are removing 3. And then we remove 3. So next what will be the answer? Is it ND4 plus ND5 because we removed required number of edges, which is 3. So is this simply the answer? Please ND4 ND5 because we are not removing this. So we add the second part where this is a function of 4 comma 0, answer for 4 comma 0, and ND5 is function of 5 comma 0. So is this a final answer? No, because if we observe question clearly, it states that we have to can handle more than max connections. So it can have less than k also. For example, if k is equal to 3, then every node can have only at most one direct connection also. So without blindly choosing ND4, ND5, we can choose the maximum answer, right? Because we want the maximum. So D2 plus D3 plus G1, this is final, plus maximum of D4 and ND4. Because we can, if the k is 3, we can only have one direct connection also. So we can remove all the nodes also. So these three are mandatory, but these two are optional. So why optional? Because it can connect to at most that number of nodes. And for 4 and 5, we have the either choice. We can delete or we cannot delete. So it is better to take the maximum. So simply maximum of D4 and D4 plus maximum D5 and ND5. So this is the final answer. So hope you got this. And now coming to next thing. So we got that we are sorting with respect to hash. So storing only hash values will get our answer? No. Because after sorting, we want the D2 and ND2 values also. Because only then we can add in the answer, right? So instead of storing only vector of integer hash, we will store vector of pair so that when we even sort based on hash, we will get a parameter from vector where it is deleted or not deleted. So let's check the code for more clarity. So simply we are inputting the n and k and initializing dp. So why dp here? Because function of node comma 1, it can be simply memoized dash dp of node comma node boolean. So dp of node and boolean. So it is simply dp of 1if and 2 and initializing with -1 and then input all the number of edges because it is tree. So we can make sure that it is n -1 and input all the values and make the edges list and then do the DFS. So DFS we also want the parent so that no need to use the vector visited. So function of 0 comma 0 comma -1. So we are starting from node 0 and there is no parent for 0. So there is no parent for 0 and then indirectly the parent is -1 because there is no, so we will not skip anything while you are doing DFS. So it is -1 and then is parent removed? There is no parent itself, so there is no way to remove, so it is 0. So function of 0 comma 0 comma -1 will return our final answer. And then if dp of it is not equal to -1, it means that it is already found, then return the value and else answer is 0. And then this is the vector that store hash. And now we are traversing through its adjacency list and then this is the neighboring node and this is the neighboring weight. So if this is not equal to parent, then we have two choices whether to remove or not. So if we are removing, for example, if we are removing, then what is the case? It is B. So if we are removing this edge, then the what will be the answer? It will be function of the neighboring node comma 1 comma node because where the parent is node and we are removing this edge, so the boolean is 1. And as we are removing this edge, there will be no contribution with respect to this edge in the final answer because we are deleting. And what is the second case? The second case is we are not deleting this. So if we are not deleting this edge, it will be function of 0 comma node plus weight, because this will be a part of final tree, so it will be weight plus weight, and then store these both values in the vector. So we are storing these both, and then we got the vector, and then we want the number of edges that need to be removed. So let's assume that it is rem. So what will be remaining? It will be simply the maximum of 0 and the adjacency list minus k minus parent. So if each parent is equal to 1, we are reducing more, so that we are reducing very less edges because the parent edge is already removed. So if each parent is 0, then we'll simply remove the adjacency list minus k, and if it is 1, then we'll remove other also. It means that we are removing less edge because the parent edge is already removed. And then maximum y it is 0. For example, the tree is connected to one node and k is equal to 3. So indirectly, what will be 1 minus 3? It will be minus 2, which is meaningless, which means that we are not going to delete anything. So then it is better to take 0 comma max, right? So that if it is even negative, we are not removing anything. So k remaining is equal to max of 0 and that. And then sort the vector based on some comparator. So we are sorting with respect to comparator, and then what will the comparator is doing? The comparator is simply returning the hash value, because what is the hash value? The hash value is function of 1 comma 1 minus function of node comma 1 and function of node comma 0 and minus weight. So this is the hash value. So we use these two as the pair, and then we are sorting based on difference. So these both are the values that we stored in the vector, right? So that is why we stored these both in the vector, and then we are sorting with respect to comparator. For example, if we have two pairs, so what is this doing? The comparator is taking two pairs and it is returning the one with higher difference value, because we discussed that we are going to sort with respect to difference. So in this way we can sort with respect to difference, and even if we are sorting, we will have the first parameter where it is not deleted. So let's check this. For example, so what we are storing in the map, in the vector, we are storing function of a and b. So what it means? So we are storing this comma this one in the vector, and we are sorting all. So after sorting, what will be the final vector? It will be the vector where every pair, it will be sorted such that the difference is increasing. So hope you got this. And so after sorting, what will be the first one? The first one, we this is this, right? So the first one is we are not deleting, and the second one is we are deleting. So we got these both. These are indirectly, this is nd and this is d, which we discussed earlier. So without directly storing nd minus d in the vector, we simply use these both, so that we can use comparator to solve with a logic inside, and even then we will have directly these both values to get the final answer. So, and now we are traversing through the vector through its children, and if it is less than the remaining, it means that we are deleting. We must delete this. So we discussed this, right? So we are deleting this. So it is d2 and d3. So this is the second parameter of pair, because we stored this first and this second. So we won't take. So how can we access the second one from pair? It is v of I dot second. So if this is still remaining, it means that this edge must be removed. So if this must be removed, then the answer is the second value of pair. And if it is not, then we have choice. We can remove or we cannot remove. So answer is simply plus max is equal to the first one and second one. And finally return the pair. We finally return after storing in the dp of node and each parent is answer. So hope you got this. If you have any doubts, comment below. See you in the next video.